In today's tutorial, we'll be discussing how we can validate our model using the test set, as well as how we can calculate a confidence interval, a root mean squared error, and an absolute percent error for how inaccurate our model was compared to the values it should have predicted versus the values it actually predicted. Before today's video, make sure to subscribe button down below and like the video for more content just like this. All right, let's discuss how exactly we can validate our model. And by the way, this is the last lecture where we will be discussing how we can create a basic machine learning model for our housing data frame. So we are right at the end now. Since in the last few tutorials, we've been talking about how to fine tune our models. Now we're going to be actually validating our fine tuned model using our stratified test set. And so if you remember, we created a stratified test set. And let me go ahead and actually print that out here, what our stratified test set looks like. So I'll go ahead and print that out. And you see here that when we print it out, you see that we have roughly 4,000 rows. And the reason for that is because remember, roughly around 20% of our rows are going to be in our test set. And then the other 80% are going to be in our training set. So we have a total of 20,000 rows. And so it would make sense that roughly a fifth or 20% of those rows would belong to our test set. Now, remember that the reason why it's called stratified is because for our median household income, we were able to take a distribution of the median income by looking at the percent of how many people fell under particular intervals of income. And we were able to divide that up into about 5 intervals of income, and we were able to push in the correct number of values in order to have a representative sample of our overall population. And so we determined an income categorization. And so you see that we have many of these columns here. And so what we're going to go ahead and do is we're going to use our grid search object that we created, I believe, two tutorials ago. And remember, we have a best estimator property that is created during the runtime of our grid search CV. And so this best estimator is going to be the best values that we should choose for our hyperparameters based on the values that we provided. And so remember, a grid search, we have to provide a param list that we did a few tutorials ago. Let me just go ahead and pull that up very fast. All right, good. So you see here that we had an n estimators, we have max features, n estimators, and then max features again. And so in total here, we basically trained how many different models? Well, we trained 4 times 3, 12 different models. And then we did 12 and then 3 times 2. All right, 18 different models, right? 18 different models we trained in the last lesson with a cross-validation of 5, meaning that we split the data into, remember, 4 training sets and 1 test set. And then we basically interchanged those numbers every single time in order to have a new test set for our model. And so we were able to accomplish that. So in total, 90 in total we went through. Okay, so, and using that, we were able to determine what our best hyperparameters were. And so remember, our best hyperparameters were, what were the values again here? Yeah, they were max features should be at 8. And so if you remember, the max features basically says how many features should be considered when we are determining our splitting for our decision nodes. So that's how we determine that. And the n estimators is the number of trees that we should have in our random forest. So it's the number of trees that we should have in our random forest there. That's what the n estimators is. Okay, so let me go ahead and run that, and you'll be able to see the model. Let me go ahead and actually print that out there. Okay, so you see that we have random forest regressor, max features 8, and estimators is 30. Okay, so we have there our fine-tuned model in that respect. Now, obviously, there are some more things that you can do. You can do some more feature engineering, which we actually did at the beginning. Feature engineering, if you remember, is just basically adding and removing columns, creating new columns in order to better assess our model. But we did most of that feature engineering before we actually fine-tuned our model. And so you could do some more feature engineering there. But this is, a very simple fine-tuned model. Okay, so from there, we have our stratified test set. And for our x values, remember, x values are attributes or our predictors that are going into the model. What we're going to go ahead and do is we're going to take all the columns, but we're going to drop the median house value. The median house value is the column that we're going to drop because that's the column that we want our model to predict, right? And so for our y test set, we would do exactly the opposite. We would take the median house value and include that as the only column that we would include for what our model should output, right? What we would expect our model to output given our x characteristics. Okay, so we can go ahead and print that out. But again, it's very simple. It's just going to be basically all the columns here except one of them, and then just one column. Okay, so very simple there. All right, so X test set prepared. We're gonna run this through our full pipeline. So remember, our full pipeline, it does, I think, three things, or yeah, I think three things. It does a one-hot encoding, right? It does a standardization, and it also does an imputer, right? And so let me go ahead and pull that up here. Let me go ahead and pull that up. Okay, so you see here our full pipeline. It calls the num pipeline, which does the standardization. So the num pipeline, if you take a look at it, all right, so the num pipeline does the imputer. So remember, the imputer fills in missing values, and in this case, we filled it in with the median, and then we also standardize each of the values so they're within a relatively consistent range. And we can also do a min max scaling as well. A min max scaling would be more likely to be affected by outliers. And then our last one that we did a let me just pull it up. All right, good. So we did a one-hot encoding. So a one-hot encoding there. And remember, we explained that a while ago. Okay, so that's what this is doing. And we're calling the transform function on that. So the transform function. What is the transform function doing? Well, basically what it's doing is it's taking the data and running it through the pipeline and getting a new output. So it's going through each of those processes of one-hot encoding, standardization, and also the imputer to fill in missing values with a median. In this case, median is less likely to be affected by outliers. It's the most robust statistic out of all the three measures of center. Okay, so we are able to get a more prepared test set there. And for our Y values, we don't have to actually standardize them in any way because remember, the Y values are not values that our model is going to use when it's predicting. So we don't need to have them within a consistent range. Only our X values need to be within that consistent range. All right, so let me go ahead and print that out since that is a little bit different. So let me go ahead and print that out so you can see that. Let me first of all run this cell and then we'll run this one. All right, so you see that we have standardized data there. All the columns are filled. All the rows, all the values are filled rather, I should say. And so you see that there. All right, so then we can get our final predictions. Our final predictions, remember, will not be standardized. They will not be standardized. They will be Y values. Okay, so you see that they're not standardized in any way whatsoever, what the house value it thinks is going to be. Now we have our predictions. Now remember, this is new data that the model has not seen yet. This is data that the model has not seen yet. And so now that we have the data that the model has not seen yet, we can calculate a generalization error. So a generalization error, basically we're figuring out how inaccurate the model was when it's presented with new unseen data that it has not seen before. Okay. Now it may have been here. Let's talk about how we can calculate the root mean squared error. So now that we have our predictions, we want to figure out how inaccurate our predictions were. Well, how can we do that? Well, we can do that by comparing it to what the value should have been. So that's the y underscore test. So the y underscore test. And remember, there are different types of errors that we can calculate. Let's take a look at this here. The root mean squared error is the error that we have been working with the most. Let's just go ahead and calculate that one. We can calculate the mean squared error again by passing in the actual values versus the expected the actual values versus the predicted values, and then we take the square root of that in order to calculate the root mean squared error to account for to put it back in the original units. Due to the fact that when we calculate the MSE or the mean squared error, we do square each of the individual errors. Okay, so let me go ahead and run that and show you what the root mean squared error is. Now remember, root mean squared error is more likely to be affected by outliers, so keep that in mind. All right, so we got $48,000. Remember, dollars in this case because we're calculating the median house value. So our model is off by roughly $48,000 in that case, so just keep that in mind there. Very similar to the values we've been working with up to this point. All right, let's also do a confidence interval. So I want to go through all of them actually. So we calculated the root mean squared error. I also want to do a confidence interval. And then I also want to close off with a mean absolute percent error, or a MAP, as it is abbreviated. Okay, so a confidence interval. What is a confidence interval? Well, a confidence interval has basically two components to it. You can a confidence interval is one thing, but there's two components when we're talking about this whole idea of how confident we are that our data is going to fall within a particular interval. There is a confidence level and there is a confidence interval. What is a confidence level? Well, a confidence level tells us how likely it is that for any population that meets the requirements that the sample had, that the output is going to be within an interval that we have decided upon. Okay, so like for example, we can say, for example, a 95% confidence, we can say that X political party will win 49 to 51% of the vote. That's a very simple way of looking at it. What's your interval in that case? Well, it's 49 to 51%. What's the confidence level? You have 95% confidence level, right? Now, what you're saying is that you have 95% confidence that a general population will vote 49% to 51% for a certain X political party, right? So, in that particular instance, you're saying that there's a 95% confidence that any population, that the overall population, based on the sample that you've been provided, is going to fulfill that certain obligation. Okay, so that's what a confidence level is. Now, we're going to determine a confidence interval for our errors. So, we're going to determine how likely it is that for any new housing that we are predicting, how likely it is that the error between the actual value that the house price should have been versus the predicted value that the house price should have been will fall within this interval that we are going to decide upon. Okay, so we're going to determine what the confidence interval is at 95% confidence. So if you take any new house and we predict what the house value is, we are 95% confident that our prediction that the model will predict will be between this value and this value off, or meaning the error is going to be less than or greater than, but how much it's going to be less than or greater than. Okay, so that's what we're going to be doing in terms of confidence intervals. Okay, so there again, this is already programmed in scikit-learn, but let's go over the general equation. So the general equation is x bar plus minus t is actually a t distribution. So there's actually something called a t distribution, and so we're gonna say alpha divided by 2 comma n minus 1. So alpha, again, this is more statistics related, and the thing is that scikit-learn already takes care of this for us. Okay, so we don't really have to worry about this too much. But alpha basically is if we have 95% confidence, the alpha is basically the level of unconfidence, right, that we have basically. So in this case, if we have 95% confidence, alpha would be 5%. Okay, so how much likely it is that our interval, that the population is not gonna, that the population statistic that we are observing is not gonna fall within our parameter, within our interval. Okay, so it'd be like 5% for 95% confidence, and then we divide that by 2. N minus 1, n simply refers to our sample size. So in this case, it's going to be 4,000 roughly. So 4,000 minus 1. S is refers to our standard deviation. Standard deviation, if you just think about it, just from a high level, refers to how spread out our data is going to be. Okay, and there's an equation that you can use in order to find that out, and we divide that by the square root of n, or the square root of 4,000 in this case, the square root of the number of instances, and the degrees of freedom is n minus 1. The degrees of freedom is n minus 1. So that's how you calculate your confidence interval there. But again, scikit-learn does this for you. Okay, so there are basically, you can use the stats.interval, .t.interval, and what this does is it basically allows you to calculate your confidence interval, and then we'll take the square root of that in order to convert it back into original units. So we're going to have 4 parameters that we're going to be sending in. We're going to be sending in the confidence level, and so in this case, it's going to be 95% confidence, and then we're going to send in our degrees of freedom. So our degrees of freedom is going to be n minus 1. We already covered that, right? So n minus 1 is our degrees of freedom. And so with that here, we're going to say n minus 1, the number of instances. So squared errors is going to be basically a list. And so we're going to take the length of that list and we're going to subtract 1. We could also take the length of the final predictions minus 1, the length of the y underscore test minus 1. It would be the same thing. All right. And the next one is going to be log. So log is the mean of squared errors. All right, so mean of squared errors. So with the mean of squared errors, the way we do that is we take the squared errors and we would call the dot mean function on that in order to pass in that particular parameter. And then we have the scale. Scale is the standard error of the mean. In order to calculate the standard error of the mean, we say stats dot s. We call the sem function on the stats class on the stats object, and so on the stats class rather. And we're going to be able to pass in our squared errors, and that's going to take the standard error of the mean, standard error of the mean there in that case. Okay, so we pass in all of those individual parameters, and we can go ahead and run that. And the reason why we take np.square root is because remember we're taking these squared errors, right? So squared errors, and so because of that, we're going to go ahead and take the square root in order to convert back into original units. Let's go ahead and run that, and you see there that we have our solution. All right, something is wrong with this. I think it's because. All right, I just realized what it was. We didn't take the square here. All right, so now I think it's gonna. Yeah, good. Now it's the correct solution. So when we said squared errors, we did not raise it to the exponent power of 2. Okay, so yeah, so the values here with a 95% confidence, we can predict that for any population, given that it has those attributes inside California, right, which is the area that we're predicting from, given that we have all of our x underscore test, we can predict that that if we push those characteristics into the model, that the prediction of the model will be at 95% confidence in between $46,757,000 and $50,649 off what the actual house price is. Okay, so that's what it is. Okay, and you can rewind that and watch me say that again, because that's the idea behind what we're doing. Okay, because it is very important that you would understand what this interval actually means. Okay, so there you go for that. All right, the last thing that I want to do, and I just want to, since this is the last tutorial over this particular section, we are going to continue on in the next chapter. We're going to talk more about cluster sampling and all of that. But in terms of this chapter, in terms of working with our housing data frame, this is going to be our last chapter. So I wanted to discuss how to select the mean absolute percent error, the mean absolute percent error. So the mean absolute percent error is actually a very simple equation. If you remember, how do you calculate the rate of change, right, between two instances? Well, you calculate the rate of change by taking the final value minus the original value all over the original value times 100, right? And so we do that right over here. We say y sub I minus y sub I hat all over y sub I. And that's going to give you your error rate for one particular row. One particular row. Now, if you want to get the mean of the error rate, you would divide the error rates. You take the sum of all the error rates and divide it by the number of error rates that exist. And then you would multiply that value by 100, since it's going to be converting from a decimal to a percent. All right. So you multiply that by 100 there. Okay, so that's the map, or the mean absolute percent error. Okay, now if you want to calculate the absolute percent error for a single instance, you just basically follow everything past this line. Okay, if you want to calculate the absolute percent error. But if you want to calculate the mean absolute percent error, then you take the sum of all the individual errors and divide it by the number of instances. Okay, so there you go. All right, and so again, scikit-learn makes this very fast for us. We just pass in our final predictions, our test, and when it calculates the mean absolute percent error, it actually does not multiply it by 100, so it's going to leave it as a decimal. So I'm going to go ahead and multiply it as by 100, and then I'm going to go ahead and print out the map, or the mean absolute percent error. And when we do that, we see that our model is off by, let me go ahead and do something like this. Percent. I'm going to say for our model will be off. Our model is off by 16%. So there you go. That's a more succinct way of writing it. Okay, so there you go. So 16.22% roughly. All right. And so there you go. So that's how inaccurate our model is based on the test set. Okay, so again, this is based on our test set that we have. All right, so there you go. There is the end of basically working with our model. We were able to get a model that has a mean absolute percent error of 16%. One last thing I want to say about mean absolute percent error versus root mean squared error is that mean absolute percent error is less likely to be affected by outliers compared to the root mean squared error, since in the RMSE, or the root mean squared error, we take the square of each of the errors. And so thinking about the square, for instance, let's say you were to have an error of 5 and an error of 10. Well, if you square an error of 10, what are you going to get? Well, you're going to get 100, right? If you square an error of 5, you're going to get 25. So even though the error was only double, when you square the values, it actually quadrupled, right? And so the mean squared error actually will, if there's an outlier, so for example, let's say the error was 100, whereas most of the errors, like let's say around 25, that outlier would be much more representative. And so it could kind of throw us off a little bit, okay? But the mean absolute percent error is not like that at all, since we don't square them at all. Okay, so keep that in mind. That's one of the reasons why you may use the mean absolute percent error, or the MAP. All right, so that is the end of this. I hope it was a good chapter, and we will come back in the next tutorial and discuss about how to do cluster sampling. So this was the full tutorial series, basically over that part of our tutorial series. In our next lesson, we will begin a new section where we will talk about cluster sampling, and we will see you in that tutorial. Make sure to subscribe button down below, like the video, and I'll catch you guys in the next video.